Okay, good evening and welcome to our today's session. We'll start by loading our data set from the R base, which is empty cars. So we can just see the history about the database, the data set that we're going to use today. So here is go to the help. Once you load this data, you run this data here in R. By running here, now you can be able to see it under help. So when you go to help, you can see the description about the data. And the data was extracted from the 1974 Motor Trend US magazine, and it comprises fuel consumption and 10 aspects of automobile design and performance of 32 automobiles of 1973, 74. So the usage, we are loading the data that is called empty cars. And the format here, a data frame with the 32 observations on 11 numeric variables. So all variables that we have in our data are numeric. And we have here descriptions about our variables. For our variables here are categorical, and we'll be able to look into that. So we'll start by viewing to display some few rows, some few observations about our data by head function in R with the data name. And we can see here some first few rows about our data. And from there, we can check the dimension of our data. Dimension of our data is 3211. That is the dimension of our data. That means 32 rows and 11 columns. As you've been told in the history, you can see all these are columns. And maybe we check some summary statistics about our data by using the summary function in R. We can be able to see the minimum value, the maximum value, the median, the first quantile, the third quantile, and the mean. So these are all variables we said are numeric, so you can be able to view them. If we want to view specific column, we use the and symbol, or not the and symbol, the ampersand symbol, and we can be able to choose which variable do we want to view its summary. So we select like the MPG alone, and we run again. We run again here, and we can be able to see the summary of one variable in R rather than the summary of the entire data. So that's how we do it in R, and I think I'll just leave that. It's also good for someone to know how to do that. And let me close this first so that we don't encounter errors. So like that, everything is okay. And then from there, now we detect outliers from the data that we have. For example, the MPG data column. So the MPG is the mile per gallon. So maybe we want to check if there is outliers in the miles per gallon of our data. So we start by computing the first quantile of our data, which is 0.25% distribution of our data. So we just run that, and then we check which value is it, 15.425, and we do the third quantile the same, and we check it is the 75th percentile of our data. Now we get the difference, which is what we call interquartile range, which is Q3 minus Q1. So this is just one method of checking outliers. We have other methods like the Z-score that you can use to check outliers in your data and others. So from there, now we want to check if our data contain outliers in our data. So we are going to use to create a variable known as outliers, and we assign it anything that we are going to get from the empty cast MPG column, and we are going to check if this is the lower bound. The lower bound is the difference between we said 1.5 is a constant. So let me just create here another variable. We call it lower bound. Lower bound. Maybe just something like that. We call it lower bound. And the lower bound we said is this part. This part is the lower bound. The computation of the first quantile minus 1.5 times the interquartile range. That gives you the lower bound of your data. we are checking outlier. So any value that will be lower than that will be considered as an outlier on the negative hand side of your data. That is the negative side of your data. So at the same point, we also maybe get the upper bound. Upper bound. So upper bound is the third is the third is the third plus the third quantile plus the 1.5 to the top. So that's how we do that. And then now from there we compare. So we compare the lower bound with any value, any minimum value that we have in the MPG column. Any value that is there, we compare it with every value that is there, we compare it with the lower bound. Or we also check if any value that is there, we compare it with the upper bound. So if that data or data sets, data points exist, if those data points exist, they are now going to create a new variable known as outliers. And we can just run that. We can just run that and maybe we can print that. So it only appears that there is one data point that is 33.9. Maybe we can check the maximum value we had for the MPG car. The MPG car 33.90. 33.9, that's the maximum value. And I think it is the one that seems to be at that point. So let's try to find out. So maybe we print the upper bound and see which value is the upper bound. So maybe we assign upper bound like this, and then we print the upper bound to see upper bound is what value. So upper bound is what value? Is 33.86. Upper bound is 33.86. Okay. So that tells us that. So we can proceed and before we remove the outlier, maybe we try to visualize the outlier. This is how we remove it. But let me try to see if we can visualize the outlier using a box plot. Should be here. So let me just take a copy of this and visualize the data. And sometimes the outlier may be that small that we cannot be able to just view it like that. So let me just take a copy of that data here where we have reached, which is a box plot. So box plot in R detects outliers. It is a 5-number summary, like the values that we had. The values we had, the minimum, maximum, the median, and stuff like that. So once we are here, so we can be able to use the box plot function in R, and then we call the column MPG, and then the main is the title, and then the Y label, and then we run this. So once we run this, we can be able to view our data here. So it seems that our data is clear. As much as there is that value, it is too small to be treated as an outlier from the box plot point of view. And that is good. So suppose we have outliers, we use a function here. We define a function here in R that helps us to remove an outlier every time we call it. So this function takes the data, and then from the data, it takes the column. So you specify the data, you specify the column, and this function will be able to compute the outlier for you and remove it. So we start by computing the first quantile. So that means that it will be taking the data and taking the column from that quantile, and then from there it computes it is quantile here. And then also the next one, using the quantile function in R, we can be able to compute the quantiles. We specify which type of quantile is it. This one is the third quantile because it's 0.75, which is 75%. And then from there, we can be able now to get the interquartile range. We get the lower bound and we get the upper bound the way we did in the previous examples. And from there, now we filter data. We filter out the outliers using this equation here. And then from there is where now we can return the data that will have dropped the outlier, the clean data. will be returned. So when we run this function, so this is how we are filtering the data. It's just like the same formula we had, the lower bound, comparing the lower bound and the upper bound. And then from there, we can be able to do that. And now when we run this function, start from here. So it will be able to remove the outliers in our data, and maybe we can check our data. So we can remove the outliers from the MPG by running this, remove outliers from the MPG column by running this. So we can run this. Yeah, so in case we had outliers in our data, it will be dropped. So maybe we run this to check the dimension of our new data that has no outliers. And it is 31, 11. And how many observations we had? At the first point we had 32, 11. So that means that the one observation that we found out from the computation of the outliers using the interquartile range mathematics has been dropped. This data point has been dropped. This data point, 33.9, has been dropped. So that means that now we have data that is clean, has no outliers there. And we can box plot again, and it's just the same plot that we have here. So we can box plot this one, the dim data. You just copy this name for the variable and change here from the empty cast to that new data that is clean and has no outliers. And when we run that, we can be able to see well where the outlier was at that point. So when you compare that data with the one that we had, so you can see what happened in our data. Outliers. And you see now the difference in the charts. So from the outlier detection, we can be able to do descriptive statistics out of our data. So we are going to use the original data that we had, but that's how we show how we compute outliers and handle them in our data. Then, so we create a variable known as the mean of the MPG column. We are most likely using the MPG column here. And you can still change to any other column you want to learn with. So we get the mean by using the mean function in R. We create a variable. We use the mean function in R. We call the column for that data that we are using. So from there now, when we want to combine, there's a way we can combine text and the variable using the paste function in R together with the print function in R for us to be able to print that text and the output at the same time. We may have just called here the mean underscore MPG. And we could have found the value. But when we want to print it together with an additional text, for example, the mean of MPG, then we get the value we use together with the paste. So you'll be seeing the paste function in some. Dennis, hope everything is fine.
Yes, on your side umepotea.
I was almost losing my network, but it's okay right now. I'm back.
Okay.
So can you see my
You can
screen?
proceed. Yes?
Can you see my screen?
No, it is not visible.
Okay. Okay. So let me proceed. And there you can see it.
Not yet.
Okay. There.
It is not yet visible.
Okay, then I have to leave and come back.
Okay, no
I
problem.
think from my end, it's telling me that it's visible. So let me just stop presenting.
Boy, kama mwanake
So I'm sharing my screen again. So just confirm with me that you can see that I'm sharing.
yes, it is visible.
Okay, now. So we have checked the mean, and now we can check the median using median function of our data. So it's just the same thing like checking the mean, but you're using median function. But for checking the mode, if data contain mode, we have to import to install a package in R known as modest to check for the mode. So we start by installing the package. So let me just install it. So the installation is all right. Installation is done. So it's already in use. I already have it from my system. So what we'll do, we'll be able to just create the mod. But if you don't have, you can just install the package by running the install.packages for the modest package in our data. And then from there now we can be able to create the mod using the mfv function that we get from the modest library to compute the mod of our data. That's the common appearance. And we can now output that. The mod, that means data contains several mods, which is 10.4, 21, 30.4, 15.2, 21.4. So data can have several modes. So that is common and there is no problem with that. So we proceed with the standard deviation. So standard deviation, we are using the SD function in R to compute the standard deviation. And we can print also the standard deviation the same way we did like that. If we want to compute the variance, we use the var function in R and we output our results in that way. And then if we want to compute the range of our data, we use the range function in R. You can output the range of our data. Range, remember, it is the minimum value and the maximum value. So you just compare this value, minimum value, maximum value is the range. The range should give us the minimum value and the maximum value. So for us to obtain the real range, we have to get the difference between the minimum value and the maximum value. And to obtain that, we refer to this data that has been created here with the two observations. So we refer to it and then we subtract the first value, we reference to the first index and the second index of our data for us to obtain the range of our data, which will be returned in an absolute value. So our range is the difference between the two values that the range of MPG is the difference between those two values. So what if we maybe say range is equal to, then we call the MPG2 minus MPG1. Maybe we reference like that. Maybe we see how it will behave and if it will be able to think the way we are thinking, that it should take the maximum value and subtract it with the smaller value. But range is a keyword in R, but yeah, so it has just the difference, but it's good when you're naming variables, you don't use the keyword like this is a keyword, but now I'm referencing to it as a variable, and that's why it is now returning here this value. So this is the range of our data. So that is just for learning. So range data, maybe I can just say range data, range MPG without the underscore MPG. Yeah, MPG, range MPG, I run it. And then the second one now, I also call it range MPG. Yeah, so that we can see that the MPG object not found. Okay, this is MPG. I named it wrongly. This is MPG like this. So I can run this and then run the other one as well. And there we go. So we can now proceed to the 5-number summary. 5-number summary. So 5-number summary here, we can be able to see to assign create a new variable with a 5-number summary MPG for MPG. Then we use the 5num to get the 5-number summary. 5-number summary is just the box plot. And when we run this, and we run that, so from running that, we can run print the 5-number summary of MPG. We can also do that, and then now we print the value. The values, the minimum, the first quantile, the median, the third quantile, and the maximum value that we have. So all these things have already been generated. If you remember, when we did the summary function, we were able to get that plus the mean. Yes, so from there, we go to data visualization. We go to data visualization. So how we visualize the data. So maybe I can paste all this code to the chat section before you go to data visualization. You can just paste this in the chat section. Just in case you want to run it, Dennis. So we go to data visualization. Data visualization here, we are going to cover some key plots in R. So we are going to use the ggplot2. This is a package in R that you have to install in your machine. So for you to use it, you have to make sure that it is installed. For me, it is installed already. So I can just load it from the library. We install only once. Every time you want to use it, you'll just be loading it from the library. So the simple plot that we start with the ggplot. So ggplot, first of all, we start by creating a variable, and then we call data. Remember, pie chart is usually used for categorical data. So in this data, mtcars, we are calling the gear dataset, the gear column. And then we create a table. From this, we tabulate the data. We tabulate the data by calling the table function. And from there, now we call it as a data frame, as we change the data type of the data in the table, we call it now a data frame. And then from there, now we can run this and just run we run the output, which is a data frame. Now this one, we can see here the output. We can see here the output that we have the var. These are the gears, and these are the counts. Number of gear, the vehicles with the 3 gears, 4 gears, 5 gears. And these are the counts. So we can rename this using the method we learned in the previous class about column names. So we use call names function in R, and we assign it to this variable. And then now we provide here the names that should be given to the column. And from there, like that, we run to get an output of the data that we created. This data now we create its new output with the new column names. The initial column names, which is the gears and their respective counts. So after doing that, we use the ggplot. We call the new data that we have created here, tabulated data, which is categorical. And then we use the aesthetic in ggplot to be able to reference to x, which is equal to, we are leaving our x to be blank, and then our y, we are giving it the counts. Our y, we are giving the count, and we are filling our plot based on the factors that we have here. These are the factors. So we are referring our data to be converted through as factors, the gears to be considered as factors. And then from there, we use plus in ggplot to add to ensure that we are continuing. So this is The geobus, we are calling the start to be equal to identity. They need to be identical. And the width of the chart is going to be 1. And then we add. We say the coordinates theta. These are some of the inputs that we call from the ggplot. So this ggplot, I just started, this is an advanced visualization of our data in R, because you see this visual is not, we have not used ggplot in plotting this. So you see how it is simple and it's not that advanced, and maybe the visual is not that professional. So if you want to make them very professional, we make use of ggplot. We define the theme here, void, so you can just learn more about themes that we have in ggplot. And then we define the labels for our data, the title, and then how we are going to fill our data. We are going to fill our data based on the gear that we converted here. And then now from there, we can run our pie chart. So let me just run this. And you see we have a simple pie chart there. So this just tells us that which data we cannot be able to know the percentages here yet. So you can still add a lot of things in this inside here by saying plus, you continue plus, and you can add labels to your pie chart. So you can just see from the distribution that we have gear 3 and gear 4. They are neighbors. So gear 3 has highest quantity, which was 15, and gear 4 has 12, and gear 5, that's 5. And from there, we can also see a bar chart. So we can see a bar chart view of this data. So pie chart, in this case, we cannot be able to see well the difference in terms of data. Maybe so we go to another categorical type of chart, which is bar chart. So in the bar chart also, we are going to use the data we defined above, which was the gear counts. And as aesthetic, the way we said, is equal to, we are leaving it blank, and then we are the equal to, we are assigning it to the columns, to the x-axis. X-axis, we are defining the gears to the x-axis, and then y will be the counts, and we are filling data based on the gears. We are filling the colors based on the gears, and same thing we just did, it is identical. And then we can be able to add the labels of our data. That's the title and the x-axis and the y-axis, and we are filling the color by the gears based on different colors, that is, because we have different levels of gears. And from there, we can be able to visualize our bar chart of gears. So you see gear, using bar chart is easier to interpret. You can be able to know how it looks like. So you can still zoom here to see your whole plot. You can zoom here to view your whole plot. So you can see here your plot, what you have just done. So you can close this. You can export your chart. You can define how you want to export it, as maybe an image or maybe a PDF, or you can copy it to clipboard and paste it somewhere else where you want to use it. From there, we go to box plots. From there, we go to box plot. So box plot is a 5-number summary, the one we had, but in this time round, we are going to use the ggplot. So it's from the MTCAS, and we are telling it that we want in the column, in the x-axis, we have different cylinder. We want to create different charts based on different types of cylinders that we have. And the y column, y axis should be based on the MPG, the level of MPG for each type of cylinder. And we are filling colors based on the categorical variable, which is cylinder, because it's categorical, and we are calling the box plot in this case. And then we add the labels. So we can just run this. We can just run this, and we see now we have different box plots based on the type of cylinder that we have. And from the output that we get, it seems that the cylinder 8 has some outliers at the top and at the bottom. So still you can compute the outliers the way we did in the previous at the top for you to identify those values and drop them accordingly, or choose another way of handling the outliers, because dropping is just one of the many ways of handling outliers. And then from there, we said you can also zoom here to view your plots, and you can export as well. We said that you can export here as an image or save it as a PDF and share with friends, or you can copy to the clipboard and do the reporting. And then we said we are going to scatter plot. Scatter plot is used. So the first two we looked at pie chart and bar chart, which are used for categorical data. Box plot is mostly used to check if there is outlier and distribution of data. Because while using box plot, it is a 5-number summary visual. We said that the bottom part is usually the minimum value. The first part is the first quantile. The middle part is the median, which is the second quantile, and the third quantile is this one, the top of the box, and the very top whisker is the maximum value. So that's how we interpret the box plot. And then we do a scatter plot using the ggplot. So scatter plot here, we are still using the empty cars dataset. And in this case, we are looking at the horsepower in the x-axis. That means that we are going to plot a relationship between the horsepower and the miles per gallon. And then from there, now we are going to do that distribution of data via points, which is going to give us the scatter plot. And then we give the labels to our data. That means that the data will read title of scatter plot of MPGs versus the hosepipe. And the x-axis will be labeled as hosepipe, and the y-axis will be labeled as the MPG. And then we run our R program for the ggplot, for the scatter plot, and check for the relationships that exist between our data. So when we try to zoom in this out, and we can see the kind of relationship that exists within our data is a negative relationship. So that means that as the horsepower increases, the MPG decreases. As the horsepower increases, the MPG decreases. As the horsepower increases, the MPG decreases. So that is the relationship. So there's a negative relationship within our data. So when you do some things like correlation, you can be able to identify the correlation value, which we will maybe be covered as part of this video or this class. And then the histogram, we can plot a histogram using a ggplot as well by referring it as histogram. So we start by defining the data set, assigning the x-axis, which is the MPG, because histogram is usually does the plot for our data, for univariate data, to check the distribution of data. And we define the width, the bandwidth of our data, of our bar histogram. And how we are going to fill the colors of the histogram. It will be a blue color, and the line color will be the dark color, the black color. And then we'll be able to add the title, which is the label, and then the title, and then x-axis, and also the frequency is the y-axis. And now we can run this histogram of our data, and we can see that there is an outlier that is existing to the lower side of our data, and maybe to the extreme as well. So those are some of the things that we can be able to identify from our data. And maybe we can now proceed. We can now proceed to the correlation matrix. So correlation matrix shows help us to understand the relationship that our variable of our data has. So among multiple variables. So in this case, we are going to create a variable known as core matrix, and then we compute the correlation of the empty cars data set, and then we can be able to print the correlation matrix out of this. So we run this, and we run this. So you can see here the correlation matrix. There's a lot of values here that shows the relationship between different variables. So like in the above case that we had about the hose pipe and the MPG, it was hose pipe and the MPG, I think so. We can just verify that. So hose pipe and the MPG, let me see the correlation matrix. Hose pipe. I think there is still extension in terms of the visuals that we have, but still we can be able to specify which part of data that we want to see. Let me see if I can specify here. I cannot call out there because correlation matrix requires that we have the multiple columns in our data. So maybe we'll see how we can subset that. But in this case, we will be able to see that some part of that later, because you can see that we have a lot of values here, and maybe when we plot a heat map, we can be able to visualize this data in a better way, because we expect that there is other columns here that are still extending, because it is supposed to plot the two-way visual of the relationships between all the variables that we have in our data. A two-way relationship between all the variables that we have in our data. Okay. So from there now we can be able to just install some packages that can enable us to visualize this data in terms of other visual, the correlation plot visual. So that we can see here that change. So the visual here, we start by installing the package known as core plot, and for my case is a library core plot. So library core plot is the one that I already installed it, so I can be able to load it by just running the library. If it is not installed, it will let you know that there's nothing that is found in the memory. And then from there now, I just say core plot, and then take these values, assign these values, and then the method is the circle. You can change something else that you want to view your data in that form. So you'll just run this so that we can have a visual of this data that has many inputs. You see what I'm saying? I was saying is the extension from here. These parts are omitted in our visual here. That's why you could not see. It's here at the top. Actually, it is here at the top. Yes. So we were comparing the hose pipe and the MPG, and you can see there's a very strong negative relationship. The one we saw in the previous scatter plot that we plotted about that. So maybe I can just regenerate that scatter plot and see it is a negative relationship. This scatter plot here, it was about the hose pipe, and so you see it's a negative relationship. So you can compare that value, which is negative 0.77, which is a strong negative relationship about our data. And from there now we can be able to return to our plot that we had, correlation plot. Yeah, and you can use this color scale for you to interpret the relationship that exists between data, which means that the dark colors indicate strong positive relationship, while the red deep colors indicate a strong negative relationship between your data. And then the other values lie between the color scale distribution. So you can tell the relationship that exists between your data by just doing that. And then from there, we go to the pair plot. So from here, these are advanced plots that you can have in scatter plot that I think we had reached somewhere where I can be able to paste. We had reached somewhere so that I don't copy all this code. I think we had reached to visualization. we need to start on visualization. So I think I can copy from visualization. Yeah, from ggplot here to up to yeah, here correlation matrix. Yeah, here and here. Yeah, here. Oh, sorry. It's just misbehaving. So I can copy this and I'll say equal to, just copy this. Fresh, that we don't encounter errors while running it from your end. So Dennis, is Dennis in the call?
Yes, I am in.
Yes, Dennis. Yes, can you, do you have your R open?
The problem is I'm not using my laptop because of bundles.
Oh, because of the bundles. Okay, okay. Okay, no
Yes.
problem, no problem, no problem. Okay. So we can just proceed. Hope you can see my screen.
Yes, it
So
is
I'll be
visible.
able,
I'm
yeah, so
following.
I'll be able to, okay, okay. I'll be able to send the recording and also this data source so that you can be able to interpret later, produce the same charts and see how the relationship exists between the data and the output. So from that point, we are going to some advanced plots. So the pair plot here it just does the scatter plot thing. Scatter plot we know is for between two variables, but the pair plot does for multiple variables. The pairwise relationship performs the pairwise relationship. And for you to do that, you have to install a package in R that is known as the ggali. So you have to install that package. That's why we didn't start by installing all the packages that we want, and that's why we need to know at what point do we need which package. So by that, it can help you a lot for you to know that. So start by installation of the package. For me, I already installed the package, so I'll be able to just load it from the library. And from there now compute the GG pairwise function from that package. If I was to run the GG pairwise without installing the package, it will have told me that that function does not exist in R base. So I can run that on all the variables, that I have in the empty class. So I can run that. So it is a pairwise plot. So it's a very dirty plot. So you see how it is computing. It's now doing its thing, and we wait for some minutes for it to plot because it is doing a pairwise computation of all the variables. And there we go. Is just still thinking, but there we go because it's a very heavy plot. So we can zoom out and you can zoom out like that and maybe make it entire screen. Yeah, so that is it. So it's a pairwise plot. So on the other side is showing the correlations values, the core values, the R values. And then the other side is showing the relationship about the distribution of the observation. So some of the observations, when you look at them, I can use the example like the plot we had, the HP, which is the hose pipe. When you look at the hose pipe and the MPG, we had this visual, this scatter plot, we had it before. So you can be able to use that interpretation to be able to make decisions. Some of us here does no relationship exist and they don't follow a particular flow. Distribution is randomly, this data are evenly distributed everywhere in the scatter plot. That means that there is no linearity in the data. So you cannot compute to check the relationships in your data. That means the relationship between your data is very small, especially the values whose values are like negative 0.21. These are very strong relationships between the variables that we have. Very weak relationships between the variables. For example, very weak relationship between the gear, because now gear is numerical categorical data. So you cannot use it to make a decision that there is a relationship between gear and this variable. So those are some of the things that are realistic, that they can exist. So I'll just close my plot here and proceed to another advanced plot, which is density plot, which is just like a histogram, but in this case it's density. So some of these things, ggplot, we have already looked at them. And if there is unique, it's just mostly maybe on the name and some parameters that this plot take. For example, density plot takes some parameter like the alpha 0.05. And we can be able to run this to see how it will be outputted. And now this is the density plot, shows the distribution of our data. And from the data, we can be able to tell if our data is skewed or not. And from this relationship of our data, it seems that there is skewness in our data, where majority of the observations tend to be past 225 mpg, miles per gallon. Yeah, but the data itself shows that though some observations tend to be to the tail, the right tail, but there is a majority of observation within the central point, of observation. So that's a density plot. There's another advanced plot also. So this is an advanced plot that enables us to plot scatter plots for different, like we can compare relationships between different, like more than 3 variables. One variable to be used as a category, and then the 2 variables now we are comparing them in each category. You can imagine how strong that advanced plot is. Like you say, it is plotting here, like the cylinders by cylinders. We have 3, 4 by cylinders here. We have 4, 6, and 8. So from those cylinders, we are plotting relationships between hosepipe and MPG that lie in the 4th cylinder. Which kind of relationship the scatter plot is that, and this one, the 6th one, and the 8th one. So depending on the problem you have, you may require this kind of plot, and we are using the existing data set in R so that you can even generate your visuals by your own without even the effort of looking for the data set to learn. So you can just get it from your R base. So we can also do a heat map. Heat map is a good way of visualizing data, especially the correlation matrix, the way we did for the above in the previous example. But we can still plot here a heat map using the p heat map package in R. And I already have it mine, and I'll just load it from the library and be able to plot. So this is the correlation matrix, the display number, display numbers true, that will show us the numbers, and then we do the which kind of clustering of the distance is just the Euclidean distance. So those are some of the analysis that this plot take. So you need to research on the Euclidean distance from each observations, and what does it mean in details for you to understand this. So when we visualize it, you see we have true, display numbers true. Now you can see the numbers. Suppose we say false, we will not be able to see the numbers on this plot, and maybe you can just use the color scale to make a decision. Object false is not found. It is false, capital, everything capital. It's false. And we can be able to see that the visual of our data here does not have numbers, but now we can make a decision about the relationship that we have. So I can just zoom this out. So you see how it looks like, and you can use the color scale to make a decision. So those values that are in the bottom with deep blue color shows negative relationship. Those values with the red color shows a strong positive relationship. Strong negative is deep blue, strong positive is red. And you can make a decision out of that. So when we want to view this data with the numbers into it, so we just change this to true. Everything is capital here. We're writing true. And there we go. So we have our view. And these are the Euclidean distances. this kind of hierarchical views. So from this, we can be able to see what we have here as part of our relationship in our data in this case. So those are advanced visualizations that you can use to make very appealing visuals, very pretty visuals. So sometimes you may want to group your data, maybe aggregate data based on the categorical data that you have. And in this case, maybe we want to compute the mean of MPG by the number of cylinder. For each cylinder, maybe 3, 4, 5, 6, and we want to compute to aggregate the mean. So using the fun method, which is an argument in the aggregate, we can use to compute the means for the MPGs for each cylinder. So we can do that. And when we compute, we can see here the computation of our cylinder here, this data that we have. And now, if we want to visualize the aggregated data, we can do the visualization from here. So to visualize that data, we call this variable we created here with the ggplot, and we change the data type to factor based on the cylinder. That is because it's category. And then we say y-axis will be the MPGs, that's the mean for the MPGs. And then we are going to fill our plot based on the cylinder, because there are different types. Some things here we have already covered about adding the labels on the x-axis, the y-axis, and the type of the plot. And maybe we can just run this to see the kind of visual that we have, which is a bar plot from the geobar. And from there, you can zoom out to view. We had this plot before, but we did not use aggregate. We used another method of doing that. So you can also use aggregate to compute that. But now for us, the previous one, we had the MPGs and gears, the MPG and gear. Okay, so from that point, we have visualized our grouped data. We had violin plot in Python, and these are advanced plots that I'm finalizing with. A violin plot is usually used to, it usually combines the box plot and the k-density plot to just provide us some more information about the distribution of our data. So I'm not going to interpret about this plot, but it's good for you to know how to interpret it, but it's not advisable, especially it is an advanced plot that if you don't know how to interpret it well, or someone you're sending the analysis to may misinterpret the data. So in this case, this is the kind of plot we're looking at, and it's usually based on the shape. We interpret based on the shape. We interpret based on the height, that's the length. We interpret based on the density, the width, and stuff like that. So you can just do that as an assignment to research on how to interpret that. And we can also do the advanced box plot here. Now we can do pairwise box plot based on for each cylinders and add other data points onto it. That's the advanced part of adding data points to our bar plots. And that is the end of that. And there is an assignment that's supposed to happen. So I'll stop sharing and then I'll share again the screen once I think I have the assignment. Let me just check it here. I like using Jupyter while writing my notes. So Jupyter Notebook. So I have an assignment here. So I just copy this and paste it in the R's. console, the R, yeah, and this I must comment them because they are treated as wrong input in the R Studio because they are not recognized by R. So I must comment them out, and there we go. So that's the assignment. Using the Boston dataset in R, you can be able to practice everything that we have practiced with the ggplot to visualize your data as well. So check out some of the plots that you can do based on this, and that marks the end of our today's session on R programming. Thank you.